Hey everyone, welcome back. So in our last explainer, we rolled up our sleeves and tackled Rust syntax and basic types, right? We built some real foundational muscle there. But today, we're kind of shifting gears into something entirely different, but equally fascinating. And real quick, I just want to explicitly mention right off the bat that this explainer is brought to you by Forge College. Okay, so today's goal? Drafting precise, unchangeable blueprints for the Ethereum virtual machine, or EVM. Let's dive into this. When you're writing a smart contract, you aren't just, writing code. You're actually engineering a permanent structure. And figuring out exactly how to lay out that structure, that's step one. Here's our schematic index for today. We'll be looking at the smart contract blueprint, top-level file paperwork, drafting the contract skeleton, constructors versus functions, moving from source to output, and finally, your Solidity workflow. Let's get to work.
Section 1. The Smart Contract Blueprint, a rigid structure.
All right, I really want you to start treating your Solidity source file not just as a normal text document, but as a rigid mechanical blueprint. Literally, every single line has a very specific physical consequence when it actually gets deployed. Notice the contrast here, right? Rust gave us the heavy machinery, super powerful, complex, highly expressive. But Solidity, well, it's all about precise EVM blueprints and strict layout. Why is that? Because in Solidity, every single declaration you make maps directly to the bytecode in the application binary interface, the ABI, that your transactions will eventually call. There is literally zero room for ambiguity here. You're defining the exact physical layout of your smart contract storage and the literal buttons your users can press.
Section 2. Top-level file paperwork, metadata, and imports.
Okay, so before we can build the machine itself, we gotta file the paperwork. Every good patent or engineering schematic needs some mandatory documentation at the very top. And honestly, Solidity is no different. At the very top of your file, you are going to see these two critical lines. First up, that SPDX license identifier. You can kind of think of this as the stamp of approval that pleases the auditor overlords. Now, it doesn't actually affect the bytecode your contract produces, but it keeps your linters happy and it clarifies your open source terms. Right below that, we've got the pragma line. This is where you lock in the laws of physics for your file. By declaring the exact compiler version, like 0.8.17 here, you're telling the compiler exactly which rules to apply. And this is absolutely crucial because it prevents any subtle, nasty behavioral differences if someone tries to compile your blueprint with a different toolset down the line.
Still in our paperwork section, we have our imports and custom errors. Imports are basically how you bring in external dependencies at compile time. It's essentially like you're ordering prefabricated parts from outside the factory to use in your own blueprint. And then there are custom errors, like this error, unauthorized. So the really crucial point here is that using custom errors acts as highly efficient, super cheap revert data. In the old days, developers used these long, incredibly expensive string messages to tell users what went wrong. But custom errors, they just return a tiny, efficient selector, which saves literally everybody gas money when a transaction fails. It's a total game changer.
Section 3. Drafting the contract skeleton, the physical layout.
All right, paperwork filed. Let's move to the main event and actually open up the contract declaration block so we can look at the physical layout of our machine's storage. Inside the contract skeleton, we've got three key anatomical parts. First, state variables. These are the literal storage slots of your machine, and they are allocated in the exact order you declare them. Let me repeat that. Order absolutely matters. Next up, we have modifiers. These are just brilliant little reusable pre- and post checks. You basically attach them to functions, and they physically alter the function's body at compilation time. We usually use these to enforce security rules, like checking who is actually calling the function before we let it run.
And then we have events. And this brilliantly illustrates how smart contracts communicate with the outside world. Events are kind of like the exhaust or the diagnostic output of our machine. Whenever your contract does something important, it emits an event. It's absolutely crucial for observation. I mean, it's how your front-end web application actually knows something happened. But, and here's the kicker, it is completely ignored by the internal mechanical state of the EVM. Events do not change your storage. They just leave a permanent log on the blockchain's diagnostic dashboard.
Section 4. Constructors versus functions. Execution timing. Now we arrive at what is probably the most critical distinction in our entire blueprint. We need to understand precisely when our code actually wakes up and runs. So, you have a constructor on one side and functions on the other. Think of the constructor as the spark plug on the factory assembly line. It fires exactly once, the very moment the contract is deployed, using creation time bytecode. Its entire job is just to set up the initial state, like welding the parts together. Functions, on the other hand, well, they're the buttons on the machine. They run repeatedly, they make up the runtime bytecode, and they actually form the ABI, which is essentially the menu of actions your users can take once the machine is fully operational and out in the wild.
So let me ask you a quick question. What happens if you accidentally initialize your contract's owner, like the person with all the admin rights, in a public function instead of the one-time constructor? Well, placing initialization logic in a public function instead of the constructor is exactly like leaving the master keys in the ignition of a newly built, totally unlocked car sitting on a public street. Literally anyone walking by can just press that public button, claim ownership, and drive off with your contract. No way you want that, right? Always, always lock your initial state in the constructor.
Section 5. From source to output. Compilation process.
Let's pull back the curtain a little bit here and analyze how our beautifully written blueprint actually gets physically manufactured by the Solidity compiler. Let's walk through this minimalistic reference table. It maps out exactly what happens when you hit compile. Your SPDX and pragma, well, that's metadata. It configures the tools and shapes the rules, but it has literally zero effect on the final bytecode. Imports, they bring in your types at compile time. But the contract block? Oh, that is the absolute heart of the operation. That is the only section that actually produces the runtime bytecode, the creation bytecode, and the ABI that ends up living on the blockchain. Everything else is just setting the stage.
Section 6. Your Solidity workflow assembly line process.
So, knowing the parts is one thing, but assembling them correctly? That is what makes you a professional. Let's introduce a really practical assembly line workflow for writing safe, logical contracts every single time. Take a look at this predictable 5-step sequence. You always start with step 1, metadata, then 2, imports, then 3, custom types and errors. Next, step 4, your contract state variables and constructor. And finally, step 5, your modifiers and functions. Now, you might be wondering why this exact order. Well, it's because the compiler reads from top to bottom. By writing in this sequence, you ensure the compiler actually knows about all your external parts and custom types before it even tries to build the actual functions that use them. It prevents accidental compilation dependencies and keeps your code perfectly, logically sound.
Okay, before we wrap up, I want to share a fantastic pro tip with you. When you're writing your state variables, using the public visibility modifier, like on this uint256 public value, is absolute magic. It's basically like automatically wiring up a diagnostic gauge directly onto your dashboard. Because behind the scenes, the compiler automatically generates a getter function for it and just adds it right to the ABI. You don't even have to write a separate function just to read that variable. It saves lines of code and honestly keeps your blueprint remarkably clean.
Wow, we have covered a lot of ground today. But before we go, I want to leave you with a bit of a challenge. Next time you look at a smart contract, or hey, when you sit down to draft your own, ask yourself this exact question. Which lines are becoming permanent ABI entry buttons for users, and which are the spark plugs firing only during creation? Being able to spot that difference instantly, that is the hallmark of a great Web3 developer for sure. Now, once again, this explainer was made by Forge College. For a deeper dive into this subject and to keep building your mastery of Web3 topics, I highly encourage you to go visit forge.college. Keep questioning, keep building, and I will see you in the next explainer.